Well, welcome, Rachid Alami, our first invited speaker at KR 2020. Rachid is a senior scientist at CNRS in Toulouse, and he's also the chair of Cognitive Interactive Robotics at the new Artificial and Natural Intelligence Toulouse Institute, which is one of only 4 new institutions to lead AI research in France. Rachid is very well known in the community. He has written numerous highly cited papers. For what it's worth, he has over 10,000 citations on Google Scholar, distributed over many interesting papers. He also has received a variety of best paper awards. And he does have a particular interest in sharing research with the general public. His research interests in particular are robotics and artificial intelligence, with a specific interest in human-robot interaction and coordination and cooperation. And as you can see, this is also what he's going to talk about today. The title of his presentation, as you can see, is Models and Decisional Issues for Human-Robot Joint Action. Join me in welcoming virtually Rachid Alami. And Rachid, on to you.
Thank you. Thank you very much. Hello, everybody. Thank you very much for the organizers. Thank you, Michael, for this and excellent presentation. So I'm very happy to be here and to share with you, and honored to share with this audience the slides I'm presenting and the talk. And well, my idea essentially is to illustrate some aspects linked to human-robot joint actions and convince you, if possible, of the interest of entering this field and working in order to endow our poor robots, poor interactive robots, with powerful decisional abilities. So this is the title of my talk, and the topic on which I've worked for years. I worked also on other aspects, but recently I focused on this aspect, which is the cognitive and interactive robot, and which has somehow the duty not only to do its part of the job, but also to be transparent, to be legible, to be acceptable, in one word, to be pertinent when doing collaborative tasks with the human. Of course, the application that we can imagine after that in the future are the service and assistant robots, which do not exist today, even if some people say they do not, and the teammate robot in the factory. At least the robots I want to speak about, the robot equipped with this high-level decisional abilities. And just to mention, this is not a work by myself alone. Around 24 PhDs have worked with me on these topics, plus other colleagues, and also a number of postdocs. And this is the work also, of course, colleagues from my lab and other labs in Europe, particularly, and also elsewhere. Now, I want to make some, I would say, preliminary introduction to this problem to illustrate this issue of the interactive robot. In fact, in robotics, we are somehow going from the autonomous robot to the collaborative robot. And in fact, autonomous robotics was for years in the robotics community and robotics and AI community, it is even today, and it will stay still for a time, a dream and a challenge. And the idea was that the robot was alone, okay? Like this one, for example, alone and far and isolated, okay? And we wanted it to be very capable. We wanted to build it so that it was very intelligent, of course. And also, the idea is you give it a task or a goal without too much details, okay? And it will do the job, okay? Solve the problem and do the job. and then it will die in the mission or be ready for another adventure. It was this kind of robot, of hero, okay? The lonely hero. But now there is another kind of robot, the robot operating in human environment. And somehow I will try to convince you that it's a new era of inquiry, because we are going from robot tools that are doing things for us to robots that are doing things with us. And the issue here is to understand, to implement, to deploy this social side of the robot somehow. Okay, I put social side between quotes so that we can discuss about it. And now, when it comes to human-robot interaction, and this really happened to me when I started to work on this, I thought we have a forerunner, and this forerunner is this guy. Why? Look at this. This is, as you will see, a kind of mobile service robot, okay, that is used here to deliver a task, to perform a task. And what you will see all the problems that we have and we should not do, all the things that we should not do. We explain to the human in detail. We calibrate the human, okay? They calibrate the human to do the task, as you see. And now the robot performs its task, okay? And it surprises the human from time to time because it's not predictable. It has its own rhythm, and the human has to comply. As you see, the human is still surprised from time to time by this rigid sequence that seems good a priori. The task is good. The machine decides by itself what's next, what's good for him, for this guy. This is a proud engineer, always proud. It's an issue also. And there we see a number of problems now. You will see that speed is not that adequate in some situations. You could see also that well, something happened here, calibration problems, perception problems, but still the high-level task is still working. There is issue of acceptability, perhaps. Yes, there is. And well, perception was needed. It was not there, but still, you see, high-level task is still working. The protocol, the high-level protocol is working, but now, consequences of small details of errors can be quite bad. But the high-level task is still working. And then, of course, you have the finale, okay? The fully autonomous machine, but it's not what we wanted, of course. So I found out also that a number of young people do not know this video, this film, so I show it. It's a modern time. It's very interesting because it was shot in between 32 and 35. The premiere was in 36. And you can see in it a number of key issues we are dealing with in human-robot interactions today that already was mentioned there. The issue of proximal interaction. Okay, human and machine are working really together, sharing space. The issue of initiative taking. Who is taking the initiative? Issues of adaptation to human. Issues of pertinence of choices and decisions. Who decides what is pertinent? Reliability, of course, fault tolerance, safety, etc., etc. So this takes us to this issue that you add a parameter somehow, the human, and in fact, you have to revisit, because you have to take him explicitly into account, to revisit the robot decisional abilities. And the robot at different levels, at planning, but also at execution, at situation assessment and interpretation steps. And this is essentially our problem, I would say. And for this, in fact, we need, even if now the human is here, and it seems simple, we need more intelligence for the robot because of this difficulty of the decisions linked to all this, and sometimes more subtlety also from the robot, but also perhaps from its designer. Now I have also some good news for young researchers entering the field. Okay, we have nothing is fully solved or finished. we have just started to scratch the surface of the things. There are a number of interesting problems, and I will try to convince that there are some that could interest you. I'm not speaking about the low-level HRI, you know, the sensory motor functions. These robots today exist, and this is absolutely necessary. I'm giving here these examples here of a robot that is able to reduce injury risk and adapt. This person is Sami Adadin. He is full professor today in Munich. He is still able to answer simple questions, even after that. He's a good friend of me too. But now what is interesting is that this robot today, we can really now put the human and the robot and make them share the environment, because they are already sufficiently safe and sufficiently for that. But this is at the low-level sensory motor level, not at the decisional level. And now we are going to our topic. The topic is basically this: building an integrated approach that will allow us to incrementally and progressively build a coherent framework for joint human-robot activity, where the robot will take the right decisions, okay, and behave in a way that, as I said, is pertinent, acceptable, etc. And this is based on a number of sources of inspiration. I think they are very, very, very interesting and still very pertinent today. Aspects developed by our colleagues. I was from them also at that time, on multi-agent BDI dialogue systems. I'm citing some of them here. Very, very interesting, and it's interesting to read again these papers. But there is also very interesting work from and inspirations from development psychology, like Michael Tomasello and others, and also from a very interesting community, which is the joint action community. There is an error here, who essentially study these issues of human-human joint action. And here you find philosophers, you find psychologists, you find development psychologists, people from ergonomy, etc., are working on these topics. And this was so interesting that we have created a series of workshops that we co-locate. Perhaps we have to do one with KR once in the future, where we gather people from this different and scientists from these different communities and make them exchange and work. If you go to these links, you will even find a number of, I think, very interesting presentations and slides from people from these different communities on this topic of human-human joint action and human-robot joint action, how we can make the link between these two, I would say, topics. I'm coming now to this concept of joint action and the mechanisms. The idea is the following. Of course, we very often engage in joint action with other humans. And we are very good in that. And we are able to do this. We are able to, there are a number of, and the joint action community studies the social interaction that happens when humans coordinate in space and time their actions and performing this activities. But now things can go right, okay? Like this, for example, because of a wrong decision somewhere, because of a wrong synchronization, because of a wrong estimation or compliance with the other, etc., etc. And here comes our aspects. We want to introduce the robot in the game, okay? And so the robot having to perform joint action, achieve joint actions with humans in different contexts. And so the question here is, how are we humans able to collaborate successfully, and what is necessary to introduce in the system so that the system becomes a good partner somehow? We are very good in detecting good and bad partners, as you know. So this is the challenge of building decisional processes for this kind of robots. There are a number of studies, of course. There are issues linked to the high level, I would say, task planning and decision level, the low level refinement and shared proximal execution, when now times becomes constraint and space becomes constraints. We are very good also ourselves to detect when we need simply to coordinate and when collaboration is necessary. And all these issues are important when we have to build this kind of system. this is the architecture. Well, it's a kind of conceptual scheme that we use, that I show to my students when we start the work. We have a task to perform. There is something to do with the robot and the human. And what we want to do is we want it to be performed in the best possible way, which means efficiency, of course, safety also, but it means also acceptability and intentionality and legibility. What do you have here? You have your human and the robot. There is a task in between. There is mutual multimodal dialogue between them, okay, gesture, speech, etc. There is also, and this is key, mutual observation. The robot observes the human observes the robot, and the robot knows or reasons on the fact that it is observed. Very important. The robot reasons on the fact that it is observed. And we claim that planning, online deliberation, reasoning, anticipation, proactive behavior can help for that. And one of the issues that appears here clearly is the notion of theory of mind. Okay, predicting, having the robot predicting and reasoning about human activity, but also human mental state and understanding of the task. And this happens at different levels, at the task level, but also when they have to share the space and not only the task. And so my work, what I have done with my students, and then I will give some examples simply, is a constructive approach. We are trying to build things, and essentially at two levels: at situation assessment and interpretation, okay, and at the level of synthesis of robot behavior, developing planning and motion, task and motion planning system. And the first aspect is linked to simply understanding and interpreting correctly the situation. I will give some examples. Of course, in 30 minutes, I will not have time to go in details, but I will give some, I would say some simply very quick overview of some of the results. How did we work? In fact, we essentially worked on different ingredients that allow us to build incrementally and their articulation to build a system. We worked on the control architectures. We worked on specific topics like human-aware navigation, which means navigation taking into account human present, human-aware manipulation, issues linked to affordances and how to reason about affordances when performing a task, affordances open to the robot, but also to the human. Perspective taking is a key aspect because it's the basis to build a theory of mind system. The robot has to reason on the perspective of the human and put itself in the shoes of the human. And then we worked also, of course, on high-level planning, like human-aware task planning, and also how the robot should cooperatively achieve a task with human and coordinate with the human. And we have applied this in different contexts, like this is a robot guide at Schiphol that embedded effectively a number of these abilities: an assistant robot at home, a robot performing some kind of information and entertainment, but also a teammate robot in a factory. Of course, this is a factory in the lab, but we have worked with industrial partners in order to have a realistic, I would say, test bed. Under the hood, there is an architecture. There are components that are combined and articulated. I will not go into these details. There are papers on this in which one can see. I will give simply examples, and the examples are essentially oriented about the models. Why? Because permanently the robot in this kind of situation have to ask itself what to do, because sometimes it's not the robot, it's what to do now, okay? Who will do? Sometimes it's a robot, sometimes it's a human. Where to perform a task, seems simple, but it's very important. When also this is clear, and how. The how is really an issue because there are many ways to perform a task, and some are far better than other, and I will show some examples about this. And this happens at different level of abstractions with various time horizons. And the issue here, as I mentioned, is the quest of models. So I will show some of these models that we have worked on. These models allow us then, when we have models, to do cost-based human-aware task and motion planning, to look at this issue of mental state and embedding communication and legibility into the action. Also reason about what the robot will do, but also what the human would like to do and can do in the interaction. I will switch here. So I'll go now directly to the examples. The first one is this issue of a situation assessment and theory of mind. Perspective taking and affordance is key in interaction between human and robot. I'm giving an example here, very simple. You know, in some situations, depending on your point of view, you don't see the same thing. And it's an issue when you have to do a task together with the guy that has another perspective. And it is important for the robot to have this ability in order to perform correctly the situation assessment and to estimate the perspective of the human. This is a very simple example of this. As you see here, we are modeling the perception of the human besides the perception of the robot. And based on this, we are computing, using spatial reasoning, the mental state, the beliefs of the robot, but also an estimation of the mental state of the human concerning the environment, where the objects are, what can I take, etc., etc. What is the robot can estimate what is hidden to the human, what is reachable to the human, etc., etc. And it's a first level of an implementation of a theory of mind, at least here for the, I would say, for the task status somehow. And I will give example. We tried to see if our robot can pass the Sally and Ann test, okay, which is a psychological test. Essentially, I think certainly a number of you know about it. If not, I will summarize it very quickly. The issue here is that you have Sally and Ann, and you show this to a child. And Sally puts her marble or her ball in the basket and leaves. Then when it is not there, Anne moves the ball from the basket to the box. And when Sally comes back, you ask the child, where do you think Sally will get her ball? And very often when the children are small, they told you there is only one truth in the box. And this is an issue that is interesting for us. So we try to implement the equivalent here. So we have a robot and two humans. Robot is red, two humans blue and green. And let's see what happens, okay? What you will see here is that perception is simplified. The robot is simply looking at tags, and from this having a 3D model of the environment that will appear in the screen. Now you see the robot is able to build the model of the environment, track the human, and see where recognize the object. What will happen now is that the robot will also build the perspective of the human, because he knows where the human is placed and where he looks back. Now a second person comes, green, who stands almost at the same place. So the robot computes almost an equivalent point of view of the human here. Okay, they see the same objects. And now, so the robot is doing this and building this set of facts and these beliefs associated to each of its human partners. Now that green has left, blue will do something that the robot will observe. As you see here, blue will take this object here and put it in a place where it cannot be seen by green if green comes back, okay? See, the robot builds, you can see at the right that the robot updates the environment. It's a little slow, but I'm living here running in normal speed. And what is interesting here is that when green comes, it will come, it's a little slow, sorry. The robot will be able to infer a number of things, okay? First, that he will infer that green is no more, that doesn't find the object who was on the table, which now you have the sphere, the green sphere. And also, oh, it stopped, I don't know why. It should not have stopped. Sorry, there was a small problem. What is important here is that it's running now. And I don't know what happens. Sorry. Okay, I will move this. And essentially, the robot will conclude that the guy is not seeing the object because it is not in his field of view, but still the robot will be able to plan, if needed, communication actions to inform the human about where the object is if it's needed for the task. So this allows the robot to reason about the perspective of the human and to integrate this in its planning and reasoning when necessary. I have another example that I will skip here that shows very quickly. I will show it here. However, the robot is using a physical simulator in order to infer what will happen with the yellow ball here when it drops from the blue box to the green box, even while not seeing it, simply by inferring using a physical simulator. So the robot is able to track also objects that are not seen if it uses a kind of physical simulator. And having this, the robot could have sufficiently, I would say, accurate estimation of the state of the world and beliefs of the human in order to perform actions like this, like give an object to a human in a place that it is visible and reachable to him, etc., etc. I will switch this because of time to go to a second aspect, since I see that I have only 5 minutes more. Elaborating a shared plan. The issue here is, in some situations, the robot has to plan, of course, but also has to estimate what will be the contribution of the human. When there is a shared goal between the human and the robot. For example, when the human gives an order to the robot, then there is a shared goal, or when they negotiate a shared goal. And what is interesting here is that we are doing this essentially by allowing the robot not only to build its stream of action, but also to estimate the stream of actions of the human. This is a kind of shared plan. And this is done also using cost-based reasoning in order to reduce the load of the human and to facilitate the work of the human. There are other issues that this is done essentially in a hierarchical way using a kind of HTN approach. And what is important here is that, for example, in some situations, like you see here and I mentioned, these two plans are equivalent in the sense that they solve the same problem. But in one of them, the human will not have to wait for the robot. Okay, and it is important for the robot to know this in order to make the human not to make the human wait for it. It's better for the robot to wait for the human than to converse. Of course, there's a kind of social interactions that could be introduced when you have to choose the good plan. This is another example of this that I will switch, where the robot builds a plan and verbalizes it and adapts it to the execution of the human. Now there are situations where, like here, as you see, the task has to be shared. It's simple handover, but in some situations the human cannot reach. And so the robot has to plan if the human has to move to reach a place where to perform the handover. It's an example here where the robot has to decide or to propose proactively where to perform a task. And this is based, again, of a number of hidden computation about accessibility, comfort of the human, issues that can be introduced in the model to perform a cost-based task planning situation. And having this, you may have situation like that where if you have a strong guy like this who is in a hurry, the robot will hand over the object only like this. And if you have an old person that accepts the robot to be intrusive, the robot will do this kind of behavior. So this is also very important because you have to equip the robot with the ability to balance between these aspects. I'm sorry, I have now to almost conclude. Yes. So I will.
How can I help you?
Okay. sorry, I will stop here and switch to the conclusion. This was another example showing that here the robot, but I will not show the details. The robot here is computing the perspective of itself and of the human here to guide him. So he will choose a place where they both can see a landmark before discussing about it. And this also assumes that the robot is able to compute these abilities. So as you see, I will switch a big part of my talk concerning these issues of building a good plan, as I mentioned. And there are a number of issues behind this, linked to legibility, communication, compliance with conventions, and go directly to the conclusion. Yes, I think so. I think so. It's more reasonable, which is the following. Okay. First, these are the authors that worked with me on these topics, and I'm happy with this. On these aspects, really, it appears that it is still, there are a number of very interesting problems that has to be taken into account when building this kind of robots. And I mentioned a number of issues here, which is the mutual responsiveness, the elaboration of plans that satisfy permanently and reactively the goals of the humans, the key notion of commitment. Okay, the robot not only has to commit, but also ensure and manage the commitment of its human partner, and also the consideration of human needs that I mentioned, like a number of preferences. This is, even if it is limited to contexts like fetch and carry, interactive manipulations, and associated tasks, is still very, very interesting and very pertinent, and covers a number of very interesting issues. And I just want to mention this because my idea was essentially to convey these issues of models and criteria for planning. These are a number of criteria that we have taken into account. Some are cost-based for cost issues like proxemics, visibility, effort. Others link are constraints. Other links are properties that a plan should satisfy. And I'm here simply showing the number of them that we have effectively taken into account in the planners that we have built. You know, proximity, comfort, acceptability, legibility, time also. Protocols is a key aspect because robots clearly have very often to adapt to and run and prototypical plans. I would say that humans know very well. I will finish here and stop here. Thank you.